Today is January 29th, 2025. We are doing a paper reading on an interesting research paper that has gotten quite a lot of attention these days, the DeepSeek-R1. To say that it has gotten quite a bit of attention is perhaps an understatement. It seems to be there even in popular news media. It seems to be the social conversation and so forth. So we are going to do this talk in two phases because there's a diversity of backgrounds in the audience. I would like to first give something that everybody can relate to, something that is not very technical, and but gives you the gist of what the paper is about. And then we'll peel the onion layer by layer. I'll do a second iteration through the whole topic, and this time I'll go through the paper with the high-level ideas, and finally, with some background and so forth. And finally, at the very end, for those of you who are looking for really good technical details, I might dive into the math. For example, there is a little bit of mathematics, not too much, but there is a bit of mathematics with the reinforcement learning technique that it uses, and we'll do that. So in any one of these three phases, hopefully you will find something that you would find useful. With that, let's get started. So DeepSeek is a new model that has emerged. It seems to have emerged from a group of young prodigies, young geniuses sitting there in Beijing, I believe, or China somewhere. And it seems to have been built with a very small budget. In a world where models take hundreds of millions of dollars to train, this has been trained quite literally on borrowed hardware borrowed from a hedge fund, which, and the hedge fund apparently had plenty of hardware sitting there, which they needed for their quantitative needs. So this group used that hardware, and the approximate estimated cost is about $5.6 million. That's it. Not $5.6 billion, not 56 million or 560 million, but just 5.6 million. That defied belief. How could you create the AI model so easily? And what is this AI model and how does it claim? What are its claims? We will go through it. And so we are going to understand this model in depth. We are going to, that will be the context for today. And so let's start with the TLDR, the very basics. What is it about? So what is this model trying to say? There are different audiences. If you are an AI engineer, then the TLDR for this model is quite simple. The big lesson that it brings about is reinforcement learning is awesomely powerful. And as you will see in this paper, what happens is that RL itself creates surprisingly powerful reasoning and self-reflection. It is not something that people, it was so obvious at all before this paper came out. So models come and models go. I have no doubt that 1 week has gone by since this model came out. There must be already contenders claiming to do better than this model. But while it may not remain as the best model for too long, maybe another, if it is already, perhaps it has been superseded. If not, in a very short time, some other model is going to supersede it. Nevertheless, the lasting contribution of this paper will be that it shows an unexpectedly large power in reinforcement learning. Just pure reinforcement learning, not reinforcement learning with human feedback. Standard reinforcement learning, using a certain reinforcement learning policy that this team had developed, DeepSeek had developed, that is called group relative policy optimization. That's a bit of a technical thing, we'll come to that. But the bottom line is, that's what it is. I'll just read a quote from this paper, which is, I suppose, really very nice. And it shows the feeling that the authors themselves had, the researchers themselves had. The quote from the paper is this: "This moment is not only an aha moment for the model, but also for the researchers observing the behavior. It underscores the power and beauty of reinforcement learning. Rather than explicitly teaching the model on how to solve a problem, we simply provide it with the right incentives, and it autonomously develops advanced problem-solving strategies. The aha moment serves as a powerful reminder of the potential of reinforcement learning to unlock new levels of intelligence in artificial systems, paving the way for more autonomous and adaptive models in the future." One could argue that this statement is perhaps the singular contribution and breakthrough or insight in this research paper. To understand what it is saying, if you look to the left, you will see that the model, the AI, was asked to solve a simple algebra problem. But as it was solving it, observe what it says in red. It says, wait, wait, wait. That's an aha moment. I can do them. So it goes about doing it differently after that. So the implication of this is this AI is capable of having an aha moment. And the fact that AI is capable of having an aha moment is certainly an aha moment for the researchers. I don't believe we have seen this kind of a thing before. Now, that is from a technical perspective. From a more social perspective, from the layman perspective, since the word DeepSeek has entered the zeitgeist and just about everyone is talking about it. People are for it, people hate it, people love it, people are curious what it is, and people have lots of opinions about it. What is it really going to do? There are many ways of looking at it, but I sort of thought that from a social perspective, I could summarize the impact in one statement. It raises the question, a possibility, that the era of industrial capture may be over. What do we mean by industrial capture? One of the problems ever since ChatGPT and all these big models came out, and it goes back even further to those very large CNN models and transformer models, that the only companies that seem capable of creating or pre-training those models and then taking it all the way to usefulness used to be the big companies, the Google, the OpenAI, the Meta, and so on and so forth. And that was a huge point of consternation. As you know, this has often been pointed out by the Stanford department, and Efefeli and many other professors have pointed out that this is industrial capture. What it means is academia doesn't get much chance to participate because academia doesn't have that kind of hardware. Open source doesn't have that kind of hardware. And just about, except for a handful of people who have quite a few billions lying here or there, the rest of us have to contend by just downloading and using whatever models are sort of released. And the frontier models, the state-of-the-art models, were never released. Meta made quite a contribution by releasing their Llama models, to their great credit. And Llama has been doing quite well, though there was a general belief that Llama does not quite rise up to the standard of the frontier models. Similarly for Mixtral and so forth. So this contribution, the contribution of this paper is, first, it has been trained on such a low budget. And so it has possibly led to the democratization of AI model training end to end. And possibly it unleashes open source creativity, which is really, really something big. Because I wouldn't call it low cost. Say $5 or $6 million is still a lot of money that you and I would have a difficult time affording, but it's certainly within the means of small companies and startups and so forth. And as in an interview, Perplexity CEO Evan mentioned, now it raises the question, why are we not all training our own models instead of paying subscription fees to the frontier models? And people are going to do that. So to that extent, the democratization is there. If you were to exaggerate the impact, I suppose, if this trend continues, let us hope that the cost comes down eventually to significantly low level and gets this whole thing gets accessible, so that I just put some children in the picture. Hopefully, these would be the next people who would grow up and train the model, even if they live not in very rich conditions or affluent conditions. So that is one impact that is being felt at a social level throughout the world after the coming out of DeepSeek. There was some controversy about this paper, that was it really trained on such little hardware? Maybe these people are hiding the fact that they trained it on a massive, massive cluster, but because of the embargo and geopolitical environment, they cannot talk about it. But I hear that within this week, UC Berkeley has confirmed that a model can be trained in not only that budget, but even smaller budget. And now somebody else has trained an even smaller budget using this technique for just about $300. So at the end of it, the seminal contribution of this paper is, it shows you a way of training models that is far, far less expensive than what we thought, that what has been the state of the art way of doing training of the frontier models. Now the question is, you might train it cheaply, but does it achieve the same level of performance? And that is a remarkable thing. We keep training small models here at Support Vectors. We do it all the time, fine-tuning training. We don't pre-train models unless they're very small models or CNNs and things like that. We do fine-tune a lot, but we know that their performances don't quite match that of frontier models quite often. But this model, which is, and I'll give you a sense of its size, it uses a concept called mixture of experts. And I'll go into the technical details subsequently in this talk, but it's a mixture of experts so that the sum total of parameters is about 671 billion parameters. That is as massive as it gets. Nevertheless, because it's a mixture of experts, what it also means that at inference time, when a query goes in, only a few experts, a subset of experts are activated. In particular, 37 billion activated parameters kick in. Right? So what does that mean? It has dual implications. The model is huge. If you want to use the whole big ginormous model, you do need sufficient GPU, hardware, big iron. But because it's a mixture of experts model and only 37 billion parameters, active parameters are used for any particular run of inference, it means that once the model is there in the GPU system, then the inference will run very fast because the amount of computations needed is almost 1/20th of the total number of things that you see there. So in reality, what it means is the tokens per second that come out of the model will be much, much higher. And you can see that. You can go to DeepSeek's website. Now, this model, there are many things that DeepSeek did that is amazing. First is that they're completely open sourced it. I believe it is under MIT license. They have, I am told they have released the source code. They have released just about everything. The only thing they have not released is the data that it was trained on. But most things, and they have made it very openly accessible. They have also provided distillations of this model. We have here at Support Vectors many variants of the model running. In fact, on the laptop that from which I'm presenting, it's a MacBook, we have a 70 billion parameter model running on this laptop itself. And in our inference server here in the data center, we have, I have to check, but we do have just about every size of the model running. So, and just practical, I wish we could do a demo. If time permits, I would like to do a demo. But our general experience with the model is we love it. I mean, the statements that it makes, that its performance is comparable to the frontier models, those statements do hold up. So if they do hold up, it solves a whole bag of problems. The problems that it solves are, first, data privacy problem. Your data is not exfiltrating your organization. Data privacy, I mean, it's all private. Your personal PII, and nobody is harvesting your queries. Nobody is harvesting your personal information, your patterns or anything. So you can just bring the model in-house, run it on your servers, on your laptop, whatever, and you will find that a large majority of use cases for which you use the frontier models, the commercial models, you don't need to go to the commercial models. This thing running on your laptop, and obviously I must argue that the laptops have to be powerful, but certainly your workstation more than suffices. For enterprises that have been very concerned about data privacy, confidentiality of their information and technical information exfiltration and espionage and all sorts of things, this is a godsend to have a frontier model in your own hands. The other thing that these people have done, which is of high value, is that they have created smaller distillates of the model. Now, one of the amazing things they found is the distillates that they create. They took all sorts of things, Llama, Quen, and all sorts of things, and they applied distillation of this DeepSeek model into them. They sort of distill the intelligence of DeepSeek into much smaller models. Now, our experience, we have been playing now with it for 4 or 5 days, pretty continuously, and our experience is that those distillates are also amazing. So if I were to recommend from what we have experienced this week, I would say that start with smaller distillates. If they don't work, then escalate it to higher and higher models. Because especially like we find that the 70 billion size model, which is one step below the full model, is just for us sufficing for all our purposes. So it's a bit of experience thing, and it's just amazing that you can do that now. And so those are the implications of having a model like this, which achieves state of the art. If you look at this graph, the deep blue is what this DeepSeek-R1 is. And you can see next to it, the gray pillar is OpenAI O1, which is their reasoning model. And then there are smaller versions of it, 32B and so on and so forth, OpenAI Mini. Now, DeepSeek has been creating a series of models. They started out with DeepSeek V3. And in a way, the journey starts from DeepSeek V3. We are going to make progress from there as we go into the technical aspects of it. Now, guys, all of these words, what is a model and so on and so forth, we'll peel the onion slowly. So I do realize that there are people at different levels of technical background. So rest assured that we will cover those. The other observation that this paper brought up, there's a part that is technical, there's a part that is actually fairly easy to understand. The simple thing to observe about this graph is the x-axis is how many steps of training you're giving to the model as it is going through reinforcement learning. Right? Now, reinforcement learning you do to the base model, like a pre-trained base model. In this case, they took the DeepSeek's V3 base model, and then you apply uh, the reinforcement learning. Now, one of the first things they did is that they completely turned the orthodoxy on its head. The orthodoxy used to be that you would pre-train a model, sort of unsupervised pre-trained a model on the whole junk of the web, massive, massive trillions of tokens. Once you did that, then you would apply supervised fine-tuning. And supervised fine-tuning, nobody questioned it ever since the research paper, Instruct GPT, which came out, I believe, in 2022 from OpenAI. It has been the blueprint for everyone to follow. You pre-train a model, you do supervised fine-tuning, and then you do something called a kind of reinforcement learning with human feedback. The problem with that is supervised fine-tuning requires you to create labeled data, examples to show this is right, this is wrong, and so forth. And labeled data is very expensive to create. Even more expensive to create is the human feedback data. When you want to do reinforcement learning on human feedback, that this answer was not so good, this answer is much better, and so on and so forth, and you get humans into the loop, the cost of training the model does go up. And computationally also, the traditional reinforcement techniques are brutally expensive. Right? So one of the breakthroughs that this paper does is that it does not use the base model R10, what is called, does not use supervised fine-tuning at all. Now, that is a huge statement to say that one model. So in this paper, there are two models, R10 and the R1. So R10 has not seen any supervised fine-tuning at all. And it has not gone through any human feedback at all. It has been only trained in reinforcement learning. And even when it is trained in reinforcement learning, it uses a very innovative method that DeepSeek originated called group relative policy optimization. And that group relative policy optimization is a bit of a technical thing. I'll just put it aside for now. But one of its advantages is it is not plagued with a problem of what is called reward hacking. What reward hacking is, just think of it in an intuitive sense as the AI during learning, instead of learning what it should learn, finds a cheat way to win, right? So that is called reward hacking. And that's a persistent problem with reinforcement learning situations and essentially in machine learning. And one of the nice things about this paper is that it does not suffer. The technique they have developed does not suffer from it. So that's sort of the TLDR. Now observe this graph carefully. Do you notice that as the machine learns more and more, the model learns more and more, the thinking time that it takes increases, the amount of output increases. Okay, so the amount of time and the length that it reasons increases. In other words, how should I say it best? It begins to think in a more sophisticated, more thoughtful ways without any prompting. You're not prompting it. You're not saying, oh, try your very best to think deeply or any kind of, there is no instruction that has gone into it. Completely no instruction. you're basically doing pure reinforcement learning, but you observe that as the training evolves, remarkably, the machine realizes that it needs to think more. It begins to self-reflect. It begins to have those aha moments. It begins to reason more carefully. And the fact that it can do that, you literally see a emergence. You literally see a gradual emergence of intelligence in a very spontaneous way, which is I suppose the most delightful discovery that one can take away from this paper, that it very organically evolves into the machine, and you start seeing it say aha, or you start seeing it reflect upon its own answer and say no, maybe I need to do differently, and so forth, and it starts thinking carefully. So the chain of thought way sort of comes about in the machine. That is remarkable. And that really does bring about why people are getting so excited. And like this thing says, during reinforcement learning, progressively evolves to longer, more involved reasoning progress. I will just give a noteworthy quote from the paper that captures sort of the emotion, I suppose, of the researchers. One of the most remarkable aspects of this paper, of this self-evolution, is the emergence of sophisticated behavior as the test time computations increase. Behavior such as reflection, where the model revisits and reevaluates its previous steps, and the exploration of alternative approaches to problem solving arise spontaneously. These behaviors are not explicitly programmed, but instead emerge as a result of the model's interaction with the reinforcement learning environment. This spontaneous development significantly enhances DeepSeek-R1's reasoning capabilities, enabling it to tackle more challenging tasks with greater efficiency and accuracy. And my perspective is the fact that we now see that this happens is perhaps the biggest contribution this paper has brought. As I said, quite likely this model will get superseded with other models, but this lesson will last. The other thing that we notice with this is as you train it more and more, the accuracy of this model does keep going up. Means it thinks for longer, but as it thinks for longer, its performance actually does go up. Right? Accuracy does go up on a particular benchmark. So those of you who know about system one and system two thinking, system one is an instinctive response, and system two is a much more careful, reasoned response, like thinking fast and slow, work of that's been there. So to me, it seems that it is developing a more mature form of system two thinking, just purely through reinforcement learning, which is amazing. So now what I would like to do, this was a very brief TLDR of the paper. I would like to now go back and walk through the paper a little bit more carefully. And to do that, I will do it in cycles. This paper rests, like all research papers or all breakthroughs, they rest upon a mountain of knowledge, and that mountain of knowledge, not all of us have. So for example, what's a transformer? I'll broadly assume that you know, but I can give you a quick understanding. What is a language model? What is reinforcement learning? And so on and so forth. I'll make it very brief. I don't think it would do justice to that, but we will talk about the core equations in this paper. So with that, I'm going to now share a different screen. So let me share my screen. All right, so let us now cover this paper in the more traditional way that I do cover the paper. But before I go further, would somebody like to ask a question? Any questions?
Like Asif, so I have a question on this test they have done. They got like good results on the specific ones like AIME and all that. But how do they perform on other tests? Like I think those things are not revealed. Are they performing well compared to uh, OpenAI's foundation models or the Llama?
See, our experiences in a limited, we have just done 4 days of testing. We are yet to find a situation where it is materially inferior to the frontier models. It's really very good. So, I mean, see, there are little, as we delve into the paper, you will see that there are areas in which OpenAI has a little bit of an edge. And there are areas in which DeepSeek has a bit of an edge. But to reach, see, think about it this way, 37 billion activated parameters. It's a baby model. Yet it is fighting in a class way beyond itself. It is competing with the frontier models, right? You have a 671 billion parameter model, but only 37 billion parameters play into the activation of a given query, given input. Nevertheless, it's producing results of comparable quality, more or less. Right? And people have been trying it on many benchmarks. And I think it has not so much to do with what data you trained it with or what hack you did. I think the biggest message here in the paper is that, guys, we had taken it as an orthodoxy to follow that pattern. That was that we will pre-train a model, then do SFT, supervised fine-tuning, then do reinforcement learning with human feedback. Somehow we had internalized that that is the only way to do it. I suppose these were young people, and young people have more adventurous ideas, one, and secondly, because they didn't have the resources, so they had more latitude to just experiment with different ideas. They essentially, you can think of it as an ablation study. They must have asked, what if we don't do SFT at all, supervised fine-tuning at all? What if we do a different technique of reinforcement learning? And so systematically, they have done it. Now, I don't know things for a fact, but from the conversations that people are having, I hear that these people have been at it for a very long time. They have been trying out these ideas for quite some time before they hit upon it. So they have done a lot of experiments before they got it right. So obviously, it is significant for that reason. But if anybody knows a situation where it fails really bad compared to other existing models, I would love to hear about it. So, all right, guys. So here we are. Now, this paper, the abstract, is more or less self-explanatory at this moment. It says DeepSeek-R1, incentivizing reasoning capabilities in LLMs via reinforcement learning. And I believe this statement is the one that will be remembered most. It's nice that in the title itself, they bring out the main thing they discovered, right? We introduced our first generation reasoning models, DeepSeek. So there are two models they're talking about, DeepSeek-R1 and R10 and DeepSeek-R1. Why two models? What they found is that you can create a really good model, but it doesn't have human alignment. It speaks or responds in a way that is not exactly readable, or the things don't come out in properly well formatted. And the other problem they noticed with DeepSeek R10 was that it sometimes responds in two languages. Now, you can ask whether that's a limitation or not, but it certainly does happen. Now, now, some things you can debate, like, for example, producing output in the right format certainly needs to be fixed. Some level of readability improvements is good. Now, whether answering it in just one language is a good thing or not, I don't know. There are many thoughts that can only be expressed in one language better than in another language. And maybe these machines have figured out, I don't know, I'm just speculating, that to best express some thought, why not use a mixture of languages? But anyway, that's just a hypothesis. But now R10 does that. In R2, you literally do reinforcement training to cure it out of using two languages. From what I hear, they don't quite cure the machine out of using more than one language, but it does reduce this incidence of that happening. So only occasionally does it answer using two different languages. Now, DeepSeek R10, a model, trained via large-scale reinforcement learning without supervised fine-tuning as a preliminary step. So we have talked a little bit about it. Let me not belabor the point. Let me go straight to the next page now. So we'll just look at any one pillar. Why don't we look at perhaps the first pillar? Just pay attention to this pillar and you can convince yourself that here, if you look at it, this DeepSeek, actually, it is the state of the art. It's doing better than the reasoning model of OpenAI, the state of the art reasoning model of OpenAI, right? And you can get it free. That's a big deal. Now, in this paper, what are the key contributions they talk about? There's a bit of a background to this. First is you need to sort of backtrack to DeepSeek V3. This was a paper they had published a while ago. In that paper, they had, amongst other things, taken a mixture of experts approach. So I'll just park that word, mixture of experts, and I'm going to explain it shortly, what it means. We'll talk about it when time permits. Mixture of experts. And there is also, in a prior work, they had discovered that the standard way of doing reinforcement learning, there is a technique, and I'll just, if you don't know the technique, it doesn't matter at all, proximal policy optimization. That it has a few limitations and problems. And to some extent, they believe that you could cure it if you use a GRPO, something that came out of the DeepSeek research group itself, which is group relative policy optimization. Right? So I'll park this here as one of the things that I'll explain. Despite the scary acronyms, actually what they mean are very simple things. So a mixture of experts and GRPO. So this work antedates this paper. It rests upon this prior work. And of course, a mixture of experts has been around and was the first paper, mixture of experts, I believe, was Jeffrey Hinton's 2016 or 2017 paper, long, long ago, many, many years ago. He had written the idea of the mixture of experts. It's well established. Mixtral, for example, is a mixture of experts. Now, let's look at the core contributions of this paper. In this paper, so let's look at this, the post-training. So first thing, okay, before I go into the contribution, let's rewind and look at the background. Yeah, so the traditional way was that you go and get the whole web data, think Wikipedia and whatnot. So it is a big mass of text. So this is scraping, some indiscriminate scraping of the web. Once you have gotten the text, the way these models or the so-called transformers or this, especially these the so-called LLMs are trained is quite simple. You do this. This process is called pre-training. And what pre-training says is that you do this. Suppose you have the sentence, the cow jumped over the, and then suppose you encountered a text that was like this. What you would give is, you would give this and ask the machine, can you guess what the next word is? And you give it a dictionary. The dictionary contains all the words from, let's say, aardvark to whatever the last word is, let's say, zephyr. And then what this machine would do is for every word, let's say, these words are called tokens. Though, and there's a subtle difference between a word and a token. A token can be a word piece, it can be a punctuation, it can be other things. But we will just use the technical term token. But whenever we say that, just think word. The next word prediction. What is the probability of the tokens, given the fact that so far this text has come? So your job is just to be the next token predictor. So this machine computes the probability of every one of these tokens, and you teach it to maximize the probability of the token moon, because you happen to know that the cow jumped over the moon. It is as simple as that. This is all that it takes to pre-train a model. Well, from an idea perspective, obviously the engineering implementation is horrendously complex because you need big machines, big clusters and whatnot. But this is all that you do. You for the technically inclined, last layer is a softmax, and softmax produce these probabilities. And then one of the things you do is you don't just necessarily take the most probable word, but you take, when you're generating text, you may sort of sample off that softmax. In other words, you may pick one of the more probable words, but not necessarily the most probable word. And that sort of stochasticity, that sort of adds creativity to the model. That is why these models are able to answer the same query differently the next time and the next time. And you can give it the same input and you will get different outputs every time you try it, right? So that is how the pre-training of what is so-called LLM done. After the model is pre-trained, there is a bit of a problem. Sometimes, and this is again, I'm deliberately oversimplifying or caricaturing it. What happens in reality is Let us say the question was, what's the capital of India? And the machine, you expect the machine to say New Delhi, but the machine might respond with, what's the capital of France? And the reason it might do that is because this machine in the pre-training process has encountered as many just list of questions, quiz questions, where you have capital of India, capital of USA, capital of England, capital of France, etc. Is you have these questions, and perhaps there are no answers given, and answers are given at the very, very, very bottom of the page or something like that, or not given at all. And so the machine could have, with equal probability, lean towards either telling you the answer or just reciprocate it by asking you a different question. Okay? So now you do have a bit of a problem. You do want it to align with uh, what is human expectation, and much of that, and also you want it to become friendly, you want it to become harmless, uh, and truthful, and so on and so forth. So the next two steps that you would do is you would take the model. Now this data is huge but cheap. This is cheap data because you have scraped the web. But then what you do, the second stage after pre-training was pre-train, you would do SFT. It's called supervised fine-tuning. And then you would do RL, HF, and then finally you would have the LLM, the way that we use it. This is called supervised fine-tuning. Quite a mouthful. Now, what does it mean? We'll explain that. In supervised fine-tuning, what you do is you literally take data. You say, if this is the input, then this has to be the output. Right? So, for example, you give it a question and you give it an answer. And then what you do is you train the machine to produce something as close to the answer as possible. So it is called learning by example. That is why it's called supervised learning. Supervised learning is when you show the right answers, a few right answers, and you expect it to generalize from there. So you have a table of data. Now this data, this is often called the label. And creating label data, you can't. Like, for example, this pre-trained data, you can just scrape the web. You can have trillions of tokens, trillions of words out there, and you can use this method to pre-train it. But you cannot have trillions of rows because somebody has to go and sit and create this table that given this input, this should be the output. And that makes it expensive. So this is label data, and it is expensive. Nevertheless, you create such data, not in vast quantities, but in reasonable enough quantities, maybe a few 100,000 rows or a million rows or something in that range, or even more for the frontier models. I don't know the exact number. And then you go and do further training of your model. After you have done that, you have one problem. It still needs to, it is beginning to get better, but you need to do alignment with human values for one. And the second thing you need to do is you need to not surprise human beings. Like, for example, if you ask a question, it should answer the question rather than reciprocating with another question and things like that. So what you do is you take the model, the half-baked model that has gone through SFT, and then you give it a query, and then it will emit out lots of response. Response 1, R2, so RK. And then you have humans grade it, provide feedback on it. Humans will tell which of the answers are better than others, right? And based on which ones the human beings like, then you go and do something called reinforcement learning. This word you will hear as an integral part of machine learning, and it has become very much central these days as we talk about large language models. So what is reinforcement learning on human feedback? So let me just look at reinforcement learning. Reinforcement learning is something that in the human domain, we are all familiar with. Sometimes, so one way you can do, imagine that, suppose you have to teach a child how to play tennis. Two ways of doing it. You could just say, see what I'm doing and learn the rules by observing me. And then you go play tennis. You hit the ball, the child sees it. Then you make a point that it must be within the court, not outside the court. It must go diagonal, and so on and so forth. by giving those example behavior, the machine, then the child learns. So that is learning by example. That is supervised, kind of closer to supervised fine tuning. But the reinforcement learning takes a slightly different approach. It says, all right, let's have the kid on the court. You don't tell the kid at all what the rules of the game are. But what you do is every time the child hits the ball nicely or does well, you give a reward. But every time the child gets the ball out of the court or something, you give a penalty. Well, you don't need to give a penalty. You just need to give a much, much, much lower reward or negative reward. So and you tell the child, just go maximize the reward, right? And the child now is left to figure out exactly how to play such that it gets the maximum reward. Now, the remarkable thing with reinforcement learning is if you do that, um, well, in the case of children, they might get rather tired. You're not telling the rules, and you just expect there's some mysterious rules that they have to figure out and get rewards. But in machines, the good thing is that they have infinite patience and they can keep trying and trying and trying. And internally, what they develop uh, inside there is they develop a policy model. A policy model is, in the case of a child, it is basically its conception of what is really happening. How do I get high rewards? So the policy model is essentially figuring out the tennis court. Are we together? For when a child has figured out the tennis court, really that ball should go here, and then this is the best way to meet the opponent. When she is on one side of the court, I should send ball to the other side of the court, and so on and so forth. That is developing an internal policy model or learning to play really well. That is what reinforcement learning is all about, right? So you need two things. You need a reward model, that is somebody who enforces the rule, which would be a referee, or gives or tells how well the child has done at every shot, every action. And the second thing is the child internally trains or develops a policy model. These policy models are typically written as PI. Right? That is reinforcement learning. Reinforcement learning is amazingly effective. You might say that it is tedious. The downside of reinforcement learning is it can be tedious. You have not told any rules at all, and it takes a very long time for the child to figure it out. Why waste so much time? You could have just told some of the rules. But the strength of reinforcement learning is once the child begins to figure it out, the child will not only figure out the rules of playing tennis, but may figure out things that even you don't know on how to beat you at tennis. Right? May develop very creative, very interesting techniques, and may easily one day completely beat you at tennis, no matter how good you are. And that is the beauty of using reinforcement learning. And whenever you see these games, machines beating humans at chess, at Go, and this and that, there's always a lot of reinforcement learning in there. You all are aware that the way they beat us is these machines come up with moves that none of us anticipated, right? It would be and those moves will then become famous, right? So that is reinforcement learning, by giving reward and punishment, but not telling the rules, not giving any examples at all. And in a way, the main message of this paper is reinforcement learning is awesome because while it learns, if you were to think of this machine, the model as a child, it learns to develop reasoning abilities. That is a surprising thing. Now, anyway, so that was reinforcement learning using that. So the orthodoxy was this. This is what I call the orthodoxy. Right? It goes back to a paper of 2022, Instruct GPT, a landmark paper that many of you would have read. If you have not read, it doesn't matter. But basically, this is the idea. Right. And it led to all sorts of very interesting memes on the internet. One meme that became very popular is that a pre-training creates a monster, hydra-headed monster. A supervised fine-tuning tames it down into a much more behaved monster. And then reinforcement learning with human feedback, human alignment, finally makes that monster look like a cute little face that delights you when you talk to it. Right? But behind it, of course, you start out with a monster that you have tamed down. And that's the thinking behind the orthodoxy of the Instruct GPT. So what does this paper say instead? What this paper says is, pre-training is there. You can't avoid pre-training. right? So keep this part. This part remains. This part and this part goes away entirely. You don't do SFT, you don't do reinforcement learning with human feedback for the R10 model. R10. Now, it turns out that for the second version of a refined version, you do bring in a little bit of supervised fine tuning, a little bit of feedback, but not too much. But to create a really powerful model, first what you need to do is just throw away both of these things and take this route. So you take a pre-trained model, right? In their case, they take their DeepSeek V3 base, right? So this is what you have done. You have trained it on all the trillions of tokens. I forget the exact number, 1.5 trillion or 5 trillion, whatever number of trillions it is. Just think of ginormous amounts of data. You have pre-trained it. And then what they did is something very interesting. They used a form of reinforcement learning, reward and punishment learning. Now, how it is done, reinforcement learning, that is the GRPO, technical thing in the GRPO. With this, they came up with, literally, directly, they came up with the so-called R10 model. And when they did that, they observed many amazing things. And one more thing that they did in this process, GRPO, in this paper, is that they did not even, remember that there are two things. You need a referee to tell how good the child is playing on the tennis court. That is called a reward model. Typically, reward models are neural networks themselves. Very hard to create, very expensive and computational and all of that, and prone to errors. Because what happens is neural networks learn to do something called reward hacking. They'll find shortcuts, right? So, for example, if there is a game, they will find little corner cases. Like, for example, if they have to move the pieces, a box in a rectangular area, what they might decide is they might go to the edge of the box and see whether the programmer forgot to prevent you from the box from going overboard. And maybe it will see what happens if it throws the box overboard, and maybe it will show up on the other side exactly where you want it to show up, and then it will say, I won. Right? Things like that. It's very common that when you do machine learning, you have to watch out for, especially reinforcement learning, you have to watch out for reward hacking. Or another example is you train a robot to lift something from here and to put it there. But what it might figure out is putting it there is the hard part. It has to do a lot of things. But instead, if it just picked it up from here, but just hovered over the bin and kept shaking its hands, for every time it came near the bin, it got a lot of reward. And so it will never actually put anything in the bin. It will just keep bobbing up its hand up and down and keep accumulating the reward. That's an example of reward hacking. So reward hacking has been a problem, obviously, in reinforcement learning methodologies. What this paper does is surprisingly simple. So we will go over it a little bit carefully. So now, what is their approach? By the way, we are going to talk of two models. So far, I'm only talking of the R10. And then we'll talk of the refinement called R1, which is the model that we are all downloading. And that's an interesting thing. But it's important to understand the R10 first. So what they do is that, let's look at that. Overview of the approach. Previous work has heavily relied on large amounts of supervised data to enhance model performance. In this study, we demonstrate that reasoning capabilities can be significantly improved through large-scale reinforcement learning, even without using supervised fine-tuning as a cold start, right? So you don't use supervised fine-tuning. So this is important. Furthermore, performance can be further enhanced with the inclusion of a small amount of cold start data, etc. So first we go to DeepSeek-R1 reinforcement learning on the base model. So base model is the one that comes out of pre-training. Reinforcement learning has demonstrated significant effectiveness in reasoning tasks as evidenced by our previous work. However, these works heavily depend on supervised data, which are time intensive to gather. In this section, we explored the potential of LLMs to develop reasoning capabilities without any, and this is the big word, without any supervised data, focusing on their self-evolution through a pure reinforcement learning process. We start with a brief overview of our RL algorithm and do that. And now, right away, the moment they talk of this approach, I'm told that people look at this equation and say, what is this? Right? Actually, this equation is very simple. So I will explain it in a more intuitive way. See, when, you see, this is this. Let me do this. Whenever you see, let's break it up. Whenever you see this double E symbol, E, it is called the expectation value. Expectation value, a simple way of thinking about it is that it's a theoretical construct in the limit of large numbers, but just think of it as average. If you just think of it as average, which you're familiar with, that is good enough. When you see Q from a pool of queries, PQ, this part here, what this part is basically saying, suppose I'm training the machine on 100 inputs. Those inputs are Q. And from the pool of those queries, I pick one query. So that is it. This is called sampling. This is a symbol for sampling. I'm sampling from a pool of queries. So now let's think what happens. So when you give it a query, let's say that you give a query to the model, it will produce response. What you do is you keep giving the same query over and over again. So it will produce a set of response, O1, O2, O, N, right? So N responses, right? In this particular, actually G, in this case, they say, okay, no, and let's just say N response for one query. Now, OI. Now what happens? Then, so this paper has a bit, first I'll explain what you do. What you need to know is how good are the response. You need some way amongst these responses to relative goodness of each response or each output. Now, the word relative is important. That is where the R in comes up. And the G speaks to the group of responses, group of outputs or responses. Right? So now the G and R of this reinforcement learning algorithms are explained. So what you can pick your group, like let's say 20 or 60 or something like that. You produce those many responses. Now, typically, like for example, PPO, what it would do is it would take a reward model, a referee, and a referee would say, and a referee is itself a neural network, it would say, okay, this model, how good one response is. But what they found is that for a whole variety of technical reasons, it is better not to do that, but instead give the referee a bunch of outputs and then ask it, give a relative rating to the responses, which is better, which is worse, etc. Relative, right? And there's a little bit of mathematics to it. So let us say that each of the outputs, O1, leads to a score, R, a reward, R1. O2 leads to a reward, R2 on these responses. Now, this is what some number, right? These are just numbers. So now in statistics, you must have learned about something called the z-value. What do? If you want the z-value of the rewards, you would take any value, subtract from it the mean, and divide it by the standard deviation of the standard deviation. Do you remember that, guys? Huh? X minus mu over sigma. If you don't remember, it doesn't matter. Just think that it's a way of making things relative to the population. So if you have positive value, you're above average. If you have negative value, you're below average. Right? That's what it is. So that is what they're trying to say. That's all they're trying to say in this equation. If you look at this equation that I'm boxing out in the rewards that come out, all you're doing is you're z-valuing it. And when you z-value the rewards, it is called the advantage. Advantage, AI. And now AI shows up here and here. So we will come to that because this equation is what we are trying to understand, but we'll come to that. Now, there is also this funny thing called DKL. What is this? DKL is the intuitive way of looking at it. It is called KL divergence. It is one of the staple diets in statistical learning. Basically, what it says is, I'll give you an intuitive picture. Let us say that you imagine, suppose that you're going to be in a place where it rains a lot. So you have a certain probability distribution in your mind that in January it will rain so much, in February it will rain so much, and blah blah blah. Right? For example, your expectation, your mental model for rainfall is how much. What is the average rainfall for each month of the year in Seattle? Right? So now that is it. Now suppose you happen to be planted in some place, right? And you have absolutely no idea what place is it, and you're asking this question: is it like Seattle or is it not like Seattle? Right. So what you would do is you would now observe data. How much rain was there in January? How much was in February? How much was it? And those are probabilities. What's the probability of rain? When you look at it, when you normalize it to a proportion, it's a probability distribution, right? Uh, this much probability of rain in January on a given day, this much probability of rain in February, and so on and so forth. So you will end up with a reality. But in your mind, the base question that you're asking is, how much like Seattle the weather is, right? And so to measure the how different the weather is at this place compared to the weather in Seattle is an intuitive notion of KL divergence. That's scale divergence for you, right? Now, why is scale divergence used in this policy? It is from a very simple thing. What you're saying is, see, there is this word pi, policy model. It keeps coming up, and it looks very sort of hard to or scary bit. Uh, Pi theta. What it means is that your neural network is made up of neurons. It's made up of parameters. Internally, it has a hypothesis. It has a belief that for me to get the maximum reward, this is what I need to do. So it creates some neural network inside it. At any given moment, at every step of learning, it has discovered a policy, a so-called policy model. Now what you want to do is you have a baseline policy model in mind, a reference policy model. And you want to make sure that as the machine learns, the policy model does not suddenly make big jumps from a baseline policy model. When you want to make sure of that, that it's not diverging suddenly or it is not going haywire, it is just a form of, think of it as a regularizing effect. It prevents very sudden jumps in learning or deviant, surprising changes in your notion of what the external or what the policy model should be, or how to maximize your reward. Then you add a DL, you add the scale divergence term. Basically, say don't deviate too much from a reference policy. Right? We have given you an approximate answer. Whatever your refined answer is to maximize rewards should be not too far, not too divergent from a baseline or a reference policy model. That is the explanation of this term. Now comes this term. What is this term trying to say? This term is literally coming from this advantage. So what it is saying is, let me deconstruct it here. I'll write it here. See, what it is saying is, suppose you have a policy that you discovered now, and you had a policy that you had a little while ago, the old policy, the ratio of this. Now, the question is your policy good or bad? Let us say that your policy says for a good action, right? A good action will be given by an advantage because the reward model will say that, okay, this is really good. Then what do you want? You want that this ratio, right, is greater than 1, right? You want to have a better model. The model saying that the conditional probability of producing that response should be higher for things that have a positive advantage, right? So that is all it is trying to. It's a cryptic. Now you clip it and then you put a minimum. These are just computational terms to make sure that these ratios, they don't go out of bounds, like they stay within 1 plus epsilon and 1 minus. They're close to 1. Like they shouldn't just wildly swing to any value possible. They should stay close to 1. That's all it is saying. So Go ahead. Somebody is asking a question. Okay, I don't hear a question. So basically, a simple way of thinking about it is just think the policy over the old policy times the advantage, right? And forgetting the min and the other things, etc. And this is one term, and the other term is the KL divergence, right? And this is how you train the model. So basically, what you're saying is the answers that are good, try to make it change your policy a little bit towards that, and but don't deviate too much from a reference policy. That is all that there is. Like this fancy equation, when you unpack it and deconstruct it, that's all it is saying. So that is the group relative policy optimization. I hope I gave you at least an intuitive sense of what this equation is trying to say. That's all it is. Now, the other thing they do, there is the fundamental question that, oh, okay, but what is your reward model, right? Where is your reward coming from? The reward model, it turns out, what they do is they make it very simple. They say we are not going to create a neural network for the reward. We are instead just going to use, because we are dealing with very quantitative problems, we will, for example, in the case of math, we will, we have a verifier, you can check whether the math is correct or not. And so we will use external tools to verify rule-based. It's a rule-based system, right? So you can have rule-based systems for verification. That is certainly true. If it writes code, if it says this is a code, this or that, you can literally, for example, algorithmic things, lead code problems, what can you do? You can use a compiler to verify that it is correct and that the program does yield the results that you expect, right? So they have replaced, and this is a huge simplification, they have replaced a neural reward model. That is another complicated neural network that would determine how much reward to give. And this rather hard to set up, can and opens the possibility for reward hacking and all that. Instead, they give a very simple accuracy rewards. They're saying, okay, if I ask you 11 plus 5 is 16, then I can easily verify whether the answer is correct or not. That is one way, right? Or if I give you a lead code problem, that how would you sort this box or whatever box of numbers, then I can check whether the code is correct or not, right? By compiling it and so on and so forth, by using external tools, by writing unit tests and so forth. So that is what they use for the reward model. And the second thing they do is they also look for format accuracy. So they make sure that your response always follows this. There are two sections, the think section. You must have a think section, and then you must have a answer section. After that, you must have a answer section. So you can put things here, you can put things here, right? And they check whether the format, those tags are present, whether it is doing what you expect it to do, and so on and so forth. And that's all there is, guys. There's a lot of details here, but basically that's the big idea. And when you do that, the amazing thing is it just works, right? So when you look at the performance, so the first thing that sort of surprises you is when you look at this. So look at this, and let's look at this line. So let's compare it to the first one, AIME 2024, the first benchmark. So pass one means you look at the one response. Now, generally what you do is in these things, people often take an ensemble of responses and they pick the majority vote. So it's common to do that. And then when you do that, the accuracy of the output goes up, especially in analytical or reasoning situations. So you notice that the O1 mini, which most of us have access to, I suppose, the score was 63.8 at pass one, and the full A1, the full-blown O1, which you have access to, I suppose, if you have a licensed OpenAI, was 74.4. DeepSeek achieved 71. So it's sort of in between there, right? But when you allow for majority vote, then you notice something quite interesting. This wins. Do you notice that at that particular moment, this number, 86.7, it wins? Remarkable. Likewise, same on the math, it turns out that even at pass 1, it wins. At another thing, pass 1, it doesn't do so well. It is sort of in between here. It is sort of in between here also. And live bench, it turns out that for code, the R10 is not doing so well. It actually underperforms. You notice that it's 50, which is less than both of the OpenAI scores, right? So again, the code force, you notice that it hasn't yet done so well for it. So it is win some, lose some situation. But what is more interesting is it is still within the ballpark of the state-of-the-art frontier models.
So, Asif, I have a question.
Sure.
Is it possible that they trained for these particular tests and get these ballpark numbers so that it looks better than OpenAI? How do we make sure?
That is a very good question. It is called benchmark data contamination. Did you include benchmark answers in the training data? That is the first suspicion anybody has, right? And I know, see, not many days have passed, only a week has passed, and people have been looking at it very carefully. The most reasonable belief is this is honest work. They have been careful. They have not done anything like that. It's not sloppy work. It's careful. They have done it carefully.
Instead of using AIME 2024, if we do the testing on AIME 2023, how are these numbers?
Try it out. The simple answer is try it out. And people are doing all those experimentations at this moment. But generally, the consensus is so far it is legit. It's legit and it's awesome.
Yeah, but I think the AIME type of questions, new questions which were never published, if
Yeah.
those are read and then compare against these models, see like which one gives better answers. That way, like we'll be confident with respect to
Yes. Yes.
this
Yes.
model. Yeah.
See, Zulfikar, it's one easy thing you can do. I am told that this organization called Lead Code, they keep releasing new questions either every day or every week or something. One very easy test that you can do is this model is trained. It's just sitting on your desktop. Go get the latest lead code question, give it to this model, and see whether you like the answer or not. Right? And I think who was it? Praveen or so? I think
So this
Praveen
is
tried.
Sridhar. This is Sridhar.
Say that again.
No, I'm Sridhar.
Oh, Shida. Oh, sorry. You're Shida. So Shida, you can try it out. You know, it's very easy to test. Just go to a source which keeps producing new questions every day and give that question to it. Now, one person here at Sport Vectors tried it out from what I think it is Praveen who tried it out with the lead code question is, I think, what he tried it out. And he came back saying it just works very well. It is able to answer very hard questions.
Yeah, yes, Asif, I tried for this week question actually.
Oh, you
So
did? Yes.
yeah,
Okay.
it works.
It works. So you know that goes to prove that they're not cheating or they are not sloppy. See, most of the time researchers are not cheating. They're just sometimes sloppy. They are not careful, and the benchmark data makes its way into the training data. But in this particular case, it seems obvious that they are pretty meticulous. They were careful.
Yeah. One more question. For math and code, it makes sense to use these reward models. So what about the other things without the
Yes, very good question. Very good question. So hold that thought in your mind because that is why we'll go from R10 to R1.
okay.
Right? Uh, that is literally a good segue for it. But before we go there, I want to just pay attention to this line. So look at this. This green line is O1, and this hyphen line that you see here, this green line is O1 at one response, and this line is the O1 for with the ensemble majority vote. So now look at the blue line. Blue line is R10 as it gets trained. Would you say that at the end of it, it is practically caught up with O1 at one response? Isn't it? And likewise, when you look at the ensemble result, majority vote, it not only achieves the same value as O1, but it seems to slightly exceed it. Let's just say that it pretty much is at the same level as O1, right?
Asif here. Can
Yeah.
you just explain a little bit about majority vote, please?
Majority vote is, suppose I ask you, the machine, what is the square root of 49? And you ask it to produce, let us say 20 results, and 17 of them say 7. 3 of them say something else. So you say majority is 7, so answer is 7.
Got it. That's it. Okay.
That's it. Because you do know that these LLMs do make mistakes. So see, this used to be what used to be called a prompting technique, yeah, to take a majority vote and so on and so forth. So that is it. Now comes a limitation of the, I don't know, I'm still having
So Asif, like this one, the steps, are they related to epoch numbers or what are these steps?
these are actually iterations. See, what happens is mini batches. These are mini batches of data making their way through. Each step is a mini batch of data. Remember, in neural network, the loops are given an epoch. Epoch is one entire journey through the data, and one step is one mini batch of data flowing forward, and then the back propagation or the learning taking place on one mini batch of data. That's one step. Right. So these days, people mostly mention either, they usually rarely say epochs, sometimes they do. But in this particular case, somewhere in the paper, they mention that they trained actually some of this thing for just a few epochs because they had so much data. And obviously, the compute budget is limited. So that is that. And I'm noticing that I'm having this problem of erasure. All right, maybe this is time to add a new page, or where did that one go? Give me a moment, guys. I seem to have DeepSeek-R1. Okay. Oh, yes. So now here are some limitations to this, and here are some surprises. One surprise that R10 brought is it broke many of the rules of prompting. It is quite interesting. They say it, but not only, they initially thought, okay, when we make this model better, it will go away. But then they found that this model and its successor, which is R1, is refinement, which is R1, both of them have a quality that things that we thought were good practices, like few shot learning, is a really bad idea. Right? So these are, the R stands for reasoning model. So these are reasoning. So R1 is a pure reasoning model. Let me just put it this way. R1, and this is a question someone asked, that this is all math and technical. It is true. That's a limitation of R10. R10 is a pure reasoning model. With this reasoning model, it turns out, and this was, by the way, a discovery made by Microsoft, I think in a previous paper, they found that when you are dealing with reasoning models, most of your expectations of prompt engineering just break. Yeah. If you're talking to a reasoning model, just be simple and direct. Explain your problem and what do you expect, the format of your expectation. And that is the best way to deal with the reasoning model. So obviously, one of the upheavals that this kind of models, as they enter our space now and they supersede the previous generation of models, will be that what used to be called prompt engineering will be turned on its head completely. Right? All those techniques, actually, people will realize don't quite work with this. So you need a different set of techniques. And the best technique at this particular moment that I can tell you, having experimented with this for a week, for not a week, a few days, is that just be simple, direct, articulate what your problem is and what your expectation is as simply and clearly as you can when you're dealing with reasoning models. That is the best. And forget about a lot of your, so don't do all of those things that my life depends on it, so make sure you give me a good answer, right? Or I'll be fired if the answer is bad, and all of those, that used to be the prompting, emotional prompting techniques, and few shot learning, and lots and lots of techniques that have developed. So go and rewrite your prompt engineering guidelines. That is one of the big messages that came up. But anyway, this is R10. Now people felt that R10 is good, but it had a few limitations. One limitation that it had is that it is a pure reasoning model. Limitations. It's a pure reasoning model. Number two, it has readability problems, especially when it doesn't do formatting, mixes languages. as an aside, I have a team in Bangalore in which people from different regions of India are. And sometimes when I'm in the meeting and we have a heated technical discussion, I'm from North India, and some of the team members, they will get very heated. And in the heat of their intellectual passion, they would suddenly change over to speaking in one of the South Indian languages. And I would just be quietly watching their interaction and hoping that some insight comes out of it. So I suppose that's what this reasoning model also R10 is also doing. It is using a mix of languages to solve a problem. So, but that is not considered to be a good thing. There was a bit of a human alignment, human values alignment thing, values alignment, like to be helpful and blah, 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 that you do as a safety precaution. So those are the things you need to do. So let us solve each of the problems. What they did is they said that, see, instead of starting with a pre-trained model, we will start with R10. What are the qualities of R10? That it is a reasoning model, that it is more inclined to a more mature at system 2 thinking, that you ask it a question, it will do a long set of reasoning before it goes and answers. That is the power and the strength of the R10. The weakness is if I just say hello, does it really require deep reasoning for you to give an answer? It shouldn't be. General purpose questions should require almost no reasoning but direct answers. And R10 was a bit weak, is a bit weak at general purpose questions, non-reasoning questions. So the question was, how do we do it? The other thing is, because it did things like this, readability, etc., what they said is, let's do a cold start. Let's start with R10. So we have gone from pre-training to R10. Now what we do is, we start with R10 and as a lesson that we have learned, and develop a slightly different approach to train a different model called R1, right? And which is what they do. Oh, by the way, this is the showing, this thing is what I showed before. As you train the machine more and more, interestingly, you observe that the machine learns to think long and hard and deeply, right? The length of its response goes up, right? I suppose it's saying the more garrulous you are, the better your answer would be. So that's that. And this is said in this paragraph that is the most remarkable thing. But what is even more remarkable is this thing they observe. It's the first time I've seen it observed in a research paper, is this particular gem of a thing, aha moment, that the machine seems to have aha moments. You look at this, it is trying to solve an algebra problem, and then on its own, it says, wait, wait, wait. That's an aha moment I can flag here. And the researchers also go, aha, wow, reinforcement learning can spontaneously learn to train a machine to reason like this, right? That's quite a gold. Okay, so now we have the drawbacks of DeepSeek-R10. Although R10 exhibits strong reasoning capabilities and autonomously develops unexpected and powerful reasoning behaviors, it faces severe issues. For instance, R10 struggles with challenges like poor readability and language mixing. To make reasoning process more readable and share them with open community, we explore R1, a method that utilizes RL with human-friendly cold start data. So now they will go through a 4-step process. Let's see what the 4-step process is.
Asif,
Yeah.
what is, how do they come with the aha moment?
No, they didn't have to. The amazing thing is, just by reinforcement learning, as the machine trains and trains and trains, the most remarkable discovery that they are seeing with this machine is, internally, it develops practically anthropomorphic ability to reason the way human beings do. That is why this lovely quote here, look at the thing that is written here and what they're saying. An interesting aha moment of an intermediate version of DeepSeek-R10. The model learns to think using an anthropomorphic tone. It literally on its own. So it's sort of an emergent phenomena. It begins to have its own aha moments, just like human beings. And then this comment goes on to say, this is also an aha moment for us, namely the researchers, allowing us to witness the power and beauty of reinforcement learning. And I believe when the dust has settled and other models have come up which are better than this particular contribution of this paper will still be standing. that is the first paper, first research that observed the emergence of such behavior in machines. And completely autonomously, without being in any way coaxed to have aha moments. All right, so now to a more practical model, R1. To do that, you take a more sophisticated approach. What you do is you take an approach of a little bit of supervised fine-tuning, a little bit of human feedback, 2 layers of reinforcement learning. So what they do is they first take it's like a child. Let's go back to the example of as a parent taking a child to learn tennis. What you want to do is not just give the child saying, okay, through go play and I'll tell you how good you're doing. But instead, bootstrap the journey, the learning process, or initiate the learning process by teaching just a little bit of rules, right? This is right, this is not, this is the thing. So a little bit of supervised learning in the very beginning to do sort of solve a cold starting problem. And then what you do is, then you do your reinforcement learning. Then you say, okay, now you know the rules, play, and I'll tell you how well you're doing. And you get better and better, right? And you hopefully play against a more and more challenging opponent. Right? So that human life intuition carries over to the AI also. So let's read it. Unlike DeepSeek-R1, to prevent the early unstable cold start phase of RL training from basic reason, for DeepSeek, we construct and collect a small amount of long chain of thought data to fine-tune the model as the initial RL actor. So what you say is, yes, you are fine-tuning on a little bit of this data, long chain of thought. COT data means you take some examples that, okay, if you're given this query, then this is the way you should reason through in your answer. Right? You explain it to the model. It gives the RL some initial actor. So it creates a certain character or certain baseline qualities in the model. And after that, you just go and do the reinforcement learning, right? A direct prompting. Now they tell how they collect the data. What they say is they collect the data to fine-tune the DeepSeek base as the starting point. They had some data from the past because they had the previous model, DeepSeek V3 base, which was a separate research paper. They already had data access, so they brought it. Then that also, compared to DeepSeek-R1 the advantage of cold start data is to include. So when you give it character, right up front, you tell the child, or you tell this model that just like you would tell the child that, see, out of the quote is wrong, within the quote is right, things like that. So in this case, you basically teach it these things, readability, and a little bit of carefulness with respect to for human priors, like how do you some small details like produce your answer in a particular way, right? You have a reasoning process and a summary, the way that I explained. And then you bring in reason-oriented reinforcement learning. And okay, I have only 15 minutes left, so I'll quickly go. So what you do is now you go through the reasoning reinforcement learning that you did with R10. You do all of that, and then you go through another phase. It is called rejection sampling supervised fine-tuning. You collect another set of data actually from the checkpoint, the model that you just created. From its own model, you produce some response. And from that, you just rate the response. This was better, this was not so good. And then you do some supervised fine-tuning. And then go and when you're doing this, by the way, one of the things you do is you not only bring reasoning data in the next phase. In the first part, you brought only reasoning data. You do a little bit of rejection sampling. Rejection sampling means this is good, this is not good, right? Bring positive and negative examples also, right? So that, for example, contrastive learning kind of a thing. You do that. And then finally, what you do is you again go and bring in this mix, you bring in ordinary data, not reasoning data, so that this machine becomes capable not just of reasoning questions, but answering general purpose questions like, how do I feed my cat, right? Or simple questions like that, or respond to hello. So then you mix, like you bring in a little bit of the normal data. Of course, because normal data everybody has in vast quantities, it's easy to go and mix it in the final process. And then then you go through the reinforcement learning again, now with this mix. And when you're done, you're done. And then what you'll end up with is this R1, big R1, which is 671 billion parameters. And then you go and start distilling it to make smaller models. And what they did is they not only distilled it, they went and they took all the other models that they knew of in the open source, Llama, Quen, these are all state-of-the-art open source models. And then they distilled from R1 into them. So one of the questions that came up is that suppose I want to make Quen better or Llama better. I have two possible paths. I can say, hey, let me take Llama and let me take it through the reinforcement learning process also, along with distillation. But what they found actually, and I don't think they have a good answer to that, but what they found is it is much better to just simply do distillation and distill the reasoning abilities from R1 into other open source models than to put those open source models through a reinforcement learning process independently. Right? And so they say that we leave that as open research question. The rest is benchmarks, guys. Benchmarks are just amazing. I mean, this has become a talk of the town, right? And like all great breakthroughs, it has people who like it, people who hate it, and all sorts of human reactions to it. But nevertheless, it's a now wherever the chips fall eventually, there is no denying that one lesson we all come out of it is that reinforcement learning can lead to a lot of very interesting and emergent behavior. And it is a remarkably powerful tool that we haven't exploited to the full so far in training the large language models. That is the overarching sort of a lesson to take away from it. They have tried many other things. One second before I take the question. They tried many other things. They have mentioned the techniques that didn't quite work. They mentioned the techniques that there's some limitations. One limitation that they mentioned, and I think I should point out, is very important. It actually puts prompt engineering on its head. And so that's a bit of a shocker. It is hidden there way in the conclusion. It says, when evaluating DeepSeek-R1, we observe that it is sensitive to prompts. A few shot prompting consistently degrades performance. Therefore, we recommend users directly describe the problems and specify the output format using zero-shot setting for optimal results. This is important, guys. And I have verified that just be direct, simple, and say what you want, and you'll get the best result. In fact, when they were fine-tuning this machine, they had to, when they got some of the training data, which had a few shot reasoning. I think during benchmarking, when they noticed that there was input that prompt had few shots, they had examples, they actually had to modify the prompts and take out the examples so that it does not degrade the performance of DeepSeek-R1. So just don't put examples in your prompt. Just say what you want and how you want it. That's it. So that's a basic thing. Now, this will lead to a lot of downstream work. It's happening at a furious pace. Somebody has replaced the GRPO with their own different reinforcement policy. I believe PPO, somebody is trying it with DPO, direct preference optimization. And so there's a whole flurry of activity, like all good breakthroughs. It opens the door for significantly more research, and we will see what comes out. All right, guys, so I'll take questions.
Yeah, Asif, like I have a question. Like I think you were mentioning about the distillation. So what exactly is happening in the distillation? Are they running the R1 model on top of Llama?
No. Distillation is a master teacher, like student teacher learning. Okay, let me give you a 1 minute understanding of distillation. And it's quite simple. So imagine that there is a teacher here, right? You give a question. The teacher produces an answer, right? Answer to the question. Now what the student does is, very roughly speaking, actually you don't do that. The loss function for distillation has 3 terms, but basically there is a ground truth answer, the best answer to the question. There is a student's answer to the question. Now what you want to do is, you want to decrease, you want to make AQ, the teacher's answer, converge to the best answer. You want the student answer to converge to the best answer. And you want the student answer to converge to the teacher's answer. Actually, let me use teacher. Teacher. So converge to the teacher's answer. So now in reality, what happens is sometimes you use if you can't change the teacher, then the only thing you can do is the output of the student to a query, you make it converge to the output that the teacher would have produced to that question. So you basically say, you know what, the easiest way to become good at something is to learn to produce the same answers, imitate the teacher, basically. And when you imitate the teacher, it is a great form of learning, right? You basically given a question, how would the teacher have answered it? Right? Answer it like that.
So that means
That process, when a model learns from a bigger model by imitating the bigger model in the answers, is called distillation. Because what happens is that the knowledge of the teacher, the wisdom of the teacher, I suppose, in human form, but in machines, the intelligence of the machine, the teacher machine, gets distilled into a much smaller model, which is a student model. So the idea is that the student model is much smaller and its job is simpler. It has to just learn from the teacher. Yeah, go ahead. Somebody was saying something.
Yeah, so that means whatever limitations the teacher model has will be the student model
propagated.
will
Absolutely get propagated. So see, distillation is an amazing technique because once you have trained a master, you can create a lot of distillates, smaller and smaller distillates, smaller students. But distillation is not without its own limitations.
But like here, the master is the llama.
No, master is the R1, the R1 model that you trained. And the student is the llama, the Quen, and all of these things.
Oh, but like they are the bigger models, no? This is a smaller model.
No. You take smaller models. Let's say that, look at this. Look at DeepSeek-R1 Distill Quen 1.5 billion. So what have they done? They have found that if you take a tiny Quen 1.5 billion and you use the R1, the DeepSeek-R1 as the teacher to teach the Quen 1.5 billion model, a tiny model of 1.5 billion parameters, which I suppose can run on your cell phone, right? Or at least on your laptop. This outperforms GPT-4o. Think about it. What a remarkable thing it is that a tiny model that has learned from DeepSeek-R1 now competes with the giants like GPT-4o. Isn't that a remarkable result? Right? Look at this statement. So that, of course, speaks to the power of distillation. This distillation student-teacher technique, it came out of a remarkable paper long ago from Jeffrey Hinton.
So like, can we do this? I think like this one is a 605 billion parameter model, R1, and like
71 billion, yes.
And 405 billion parameters is the llama. So can it train the bigger models also?
Yes. I mean, distillation you can apply. There is nothing put there in the math that the student has to be tinier. Generally, it's by convention. It's common way that the reason you train a smaller model to imitate the master is because the smaller model has less parameters. But nothing prevents you from taking a comparable size model and having it learn from the teacher.
So what sort of benchmarks they are using for comparing these one-on-one comparison?
They mentioned the AIME 2024 and the math. These are benchmarks. These are the names of the benchmark. Let me highlight it. Here, do you see? Hang on, let me use a pen. This one, this AIME and this math, these are benchmarks.
And how much time it takes to do this distillation? The time and the number of GPUs they have to use?
They haven't given those specific details, but through experience, I can tell you. If you're training a 1.5 billion model in a distillation, I would imagine that if you have an 8 GPU server, each of the GPUs running H200 or something like that, it wouldn't take that long at all.
And these are open source, so they have
all of them. This entire work is open source.
Even like the distilled model, the student model, like they have open sourced.
Everything is open source. Actually, the remarkable thing about this whole activity is somebody quipped, I noticed a comment somewhere on the web, that DeepSeek is OpenAI, but OpenAI is not OpenAI.
Yeah. But also like they were talking about like they were using FP8 instead of FP16, like the bigger models. Where is that information in this paper, or it's written somewhere else?
It is there. So one of the things people are realizing is that people are beginning to question whether you need full precision or not, right? These people somewhere in this, they say that FP8 is good enough.
Yeah, because when I search with FP8, I'm not able to see in the paper.
Yeah, no, it is there. It's there somewhere. I don't know where it is, but it's there.
And they were also mentioning about compression was used, so that like
Yes. See,
memory.
cache, KV cache compression, etc. All of those techniques you use, and you use this mask latent attention and so on and so forth. See, all the techniques. See, in open source, it's an evolutionary process. These guys have adopted all the discoveries, for example, that is there in Meta's Llama paper, and they refer to it. They mention it, right? So a lot of those things that Llama discovered, the Meta group discovered with the Llama training, Llama 3 training, they have adopted all of that. It becomes part of that's how research goes, right? You internalize all the best that has happened so far and you move the needle forward.
Question, Asif.
Yeah.
How big was the RL data?
It is in trillions of tokens. The RL data was not that big. Actually, the RL data, surprisingly, I think I happen to remember the number. I believe they said that they had just 200,000 instances of data, or 600,000. I forget which one, but tiny. Like compared to the millions and gazillions that people talk of, they had pretty tiny amount of data. Pre-training was, of course, in trillions of tokens. That is, but they just took the DeepSeek V3 base model from previous research. Pre-trained started from there, but the work that they did is did not take much data. Now, within this week, see, things are happening at lightning speed. I think from Berkeley verified, you see Berkeley verified that these guys are really saying that because you can train this model with limited hardware. Then another breakthrough somebody made with a different policy gradient, reinforcement idea. Oh yeah, somebody else verified with another, but a smaller model that you can get away with just 100,000 or 200,000 instances of data for reinforcement learning. So the progress on this is happening at lightning speed everywhere. It's hard to find research groups that are not fascinated by this and are not trying out.
And,
So guys, yeah, go ahead.
And people are able to find the guardrails. I think like, yeah, some of this stuff it doesn't even give any output like Tiananmen square related instance. So like, did anyone come up with a list of guardrails they have included in the model?
They have not. I don't think that has happened. It's all very fresh. But frankly, right, which of these commercial models have told you what guardrails they have put? So there is a lot of hypocrisy going around, if I may say that. Somebody pointed out that if you look at first of all, you can download the model, run it in the privacy of your home. There's no data exfiltration, no privacy issue at all. They have also hosted it on their server very, very cheaply compared to OpenAI, very almost 1/20th the cost or something like that. Now people are saying, oh, but now so much data is going to China and whatnot. And they are going to harvest the data and their security concerns. Yes, there are. But what about the fact that all the models that are being hosted commercially anywhere in the world, whether it's Mixtral in France or it is OpenAI in US, they are all having exactly the same user agreement. Everything you do with those models on their websites, they're harvesting it. Right. So, and the difference is that with R1, you don't need to go to them. You can just download it, run it in the privacy of your own home or your own office, corporate office. So there is you get absolute privacy then, right? Another story that I heard is actually it costs 100,000 GPUs or 50,000 GPUs. They're just not talking about it. I think you see Berkeley, there's already fairly conclusive evidence that that's not true. It was actually trained with very little hardware. It can easily be trained with very little hardware. Some other research groups are able to train it with even less hardware. And the most remarkable thing I heard, which I have not verified, is somebody has created a small model using this technique and trained it with just $300. $300. Think about it. With pretty good reasoning abilities. Yeah. So now there is a massive rethinking about what does it really take to train good models. And see, good research opens the door. Good research doesn't answer all the question. I don't think that this model has a chance of even lasting 1 week or 2 weeks as the best model. Right? It will get superseded by other models. It must have already gone that. I just heard that Quen Max came out from Alibaba and is supposed to be better than at least DeepSeek V3. I don't know what its comparison to R1 is, but it's supposed to be better than V3. I also just heard today morning somewhere that the without the the human alignment, the making sure it speaks in only one language and readability thing, right? Actually, the model is smarter. It loses some reasoning power when you bend it to human preferences, which you would expect. Right? So there's all sorts of interesting evidence coming around from all directions.
Yeah, I think like this particular paper is talking about like less time and like less cost and
Yeah.
like the innovation they did, and they are better in some of this AIME related stuff. But I think
Yeah.
like still they're at 70%. I think I'm looking forward for newer models to come, like which are going to give even better numbers than the 70s. Like I would like to see like 80% or 90%. I think
Yeah.
there is a lot of work. I think like
Yes, Latam.
few months
Shankar, I'm
back.
sorry, I have to interrupt you. I apologize because there is another meetup that we are hosting, and people are waiting for that. But I would like to end with a conclusion because those people have already entered the Zoom, so I apologize. We can take the discussion offline anytime, but I would like to conclude with one final thought, guys. See, 2024 and now 2025 is when we realized that we were putting a lot of energy into pre-training models, and we had the neural scaling laws for the pre-training of the model. That is still true, but our attention has now shifted towards what happens after pre-training. So a lot of the test time, inference time computes, that is where our attention has shifted, and that is the big movement that's taking place here. And this R1 falls broadly in that picture, this shift to inference time and test time compute more broadly in this AI world, right? And it's part of that. Okay, so with that, I would like to end today's session. I apologize, guys, I can't take any more questions, or maybe I'll give, but only a question, not a long one. If anybody has a quick question, I can give 30 seconds to it.
Yeah, so I have a quick question. So is it possible that the mixture of experts model is causing the language mix-up issue?
No, that has nothing to do with it.
Okay.
I mean, you could have, possibly you could say that, but I would be surprised if that were the case.
Hey, Asif, sorry, another quick question. So the disparity in cost, is it coming from the fact that they got rid of the supervised fine-tuning? Where is this exactly coming from?
It is, many reasons. I don't know. See, when a frontier model says, company says we spend 140 billion, 140 million, do you have any way of finding out where exactly that 140 million went? Was it, how much of that went into gathering supervised fine-tuning data? How much of it went into human feedback? How much of it went into compute hardware? Who knows, right? So those are questions that are somewhat indeterminate, considering the fact that these companies like OpenAI, et cetera, they are rather closed. They have a curtain of privacy around themselves. We know nothing about what they do inside. All we see is the result.
But regarding DeepSeek, what do you think this is like attributed to?
It's a very direct and simple model. See, remember, I think the simplification comes because it overthrows the orthodoxy. Remember, I said that you don't need all this orthodoxy. It doesn't do supervised fine-tuning. It doesn't do reinforcement learning with human feedback. It directly does only reinforcement learning without a neural reward model, just a rule-based model. And it does a relative ranking or relative, group relative a policy optimization. It takes the most direct and simple approach imaginable. And the most remarkable thing is, with such a direct and simple approach, which breaks the orthodoxy, it achieves the state-of-the-art results. All right, guys, I apologize. And thank you again for being part of our weekly meetup series, guys. We meet every week on Wednesday